You ever look at a computer science exam and just see a bunch of, well, gibberish? A mess of strange code and confusing questions? Today, we're going to flip that on its head. We're treating one of these exams not as a test, but as a blueprint for understanding our entire digital world. All right, let's get into it.
So really, what does it take to pass a computer science exam? I'll tell you, it's not just about cramming facts. It's about learning to think in a very specific, logical way. So think of this as a guided tour. We're using this exam paper as our map to explore the absolute core of computer science.
Okay, first things first, we have to understand how computers actually see information. And that brings us to Pillar 1, the language of machines. This is where we get right down to the nitty-gritty, the most fundamental level of how a computer represents, well, everything.
And at its very heart, that language is binary. Every single thing your computer does, every color on this screen, every sound it plays, every single letter you type, it's all broken down into a massive string of ones and zeros. Just think of it like millions of tiny light switches, each one either on or off. That's it. That's the foundation for literally everything.
Yeah, but as you can probably guess, trying to read or write these giant strings of ones and zeros is a total nightmare. It's just asking for mistakes. And that's where hexadecimal comes in. It's basically a much smarter, cleaner shorthand for those long binary codes. So a binary string like 01000011 just becomes 43 in hex. So much easier, right? Coders use this all the time for stuff like defining colors on a web page or writing down unique hardware addresses.
So how do we get from a number we understand, like 43, to what the machine gets? It's actually a pretty neat little puzzle. You just take your number and keep dividing it by 2, writing down the remainder each time. Once you can't divide anymore, you just read those remainders from the bottom up, and boom, just like that, you're speaking the machine's language.
All right, let's build on that. Now we know how computers see data, but how do we get them to do something with it? Welcome to Pillar 2, the logic of programs. This is all about how we teach a machine to, well, think.
So the big question is, how do you give a computer instructions with absolutely zero room for confusion? See, a computer has zero imagination. It can't guess what you mean. You have to spell everything out for it, perfectly. And that's where things like algorithms and structured logic come into play. And flowcharts, like this one right from the exam, are the perfect way to see that logic in action. It's a crystal clear step-by-step roadmap for a simple task. Checking the weight of some sacks. Is it too heavy? Nope, reject it. Is it too light? Reject it. If it's just right, accept it. Each step is just a simple yes or no question, something a computer can execute flawlessly over and over and over again. And that whole over and over again part, that's the superpower of programming. Coders will often sketch out their logic using something called pseudocode. It's like a simplified, human-friendly version of code before they write the real thing. This little piece here, repeat until, that's what we call a loop. It just tells the computer to keep doing something until a certain condition is met. In this case, until it's checked 10 sacks. That's how you automate pretty much everything.
So, we've got a machine that understands data and can follow instructions, but the real magic happens when we start connecting them together, and that brings us to Pillar 3, the connected world. This is where we zoom out from one single computer to a massive global network.
And right at the heart of the connected world, the internet, is HTML. Now, the exam defines it as the standard language for creating web pages, and that's spot on. But here's the key. It's not a programming language that does things. It's a markup language that gives a web page its structure. It's the skeleton that holds everything together on almost every single website you've ever visited.
And how do we find these websites? With the URL, of course. Let's break this one down. You've got the protocol, which tells the browser how to connect. Then there's the domain name. That's the website's unique address. And finally, the path, which points to a specific page on that site. It seems so simple, but that elegant structure is what makes the entire web work.
But it's not just websites that have addresses. Every single device on a network, your phone, your laptop, your smart TV, has a unique digital fingerprint called a MAC address. It's a permanent hardware ID that never changes. It's how your Wi-Fi router knows exactly which device is which, making sure your cat videos go to your phone and not your neighbor's.
Okay, so with billions of devices all chattering away, a massive new challenge appears: security. And that brings us to our fourth and final pillar, and it is a big one: building the digital fortress. This is all about how we go about protecting our digital lives. The exam makes it really clear. You have to know your enemy.
Here are two big threats that people mix up all the time. Phishing is the bait. It's that fake email from your bank trying to trick you into clicking a bad link and giving up your password. Farming, though, is way sneakier. That's when malicious code gets on your computer and sends you to a fake website even if you type the address in perfectly.
So, how do we fight back? Well, we have a few lines of defense. A firewall is like a security guard for your network, checking everything coming in and going out, and blocking anything that looks suspicious. Then there's SSL. You know that little padlock you see in your browser's address bar? That means SSL is working, creating a secure, encrypted tunnel between you and the website. And the core of all of this is encryption itself, the art of scrambling data into unreadable nonsense, making it totally useless to anyone who doesn't have the secret key.
But it's not all about firewalls and encryption. This is so important. The exam also makes students think about ethics. It's a powerful reminder that having the skill to build these amazing things comes with a huge responsibility. It's not enough to know how to access private data. A real computer scientist has to ask if they should and what the consequences are for real people.
So let's just take a step back for a second. After walking through this entire exam paper, what's the big picture here? What have we really learned? We've seen that computer science really stands on these four interconnected pillars. It all starts with the basic language of machines, then builds up to the logic of programs, expands out to the connected world of networks, and, crucially, is wrapped in a layer of security and ethics. That's the whole shebang.
And that brings us all the way back to the beginning. What does it take to pass? It's really not about memorizing syntax. It's about developing a whole new way of thinking, a structured, logical, and responsible way to look at problems. So the real test isn't about the grade you get. It's about seeing the world in a whole new way. The real question is, can you think like a coder?